If you've ever searched for how ChatGPT works, you've probably come across words like transformers, attention, embeddings, LoRa, or QLoRa. At first, they can feel complicated and completely unrelated. But what if I told you that many of these ideas are connected by a single concept from linear algebra? That concept is matrix rank. Don't worry if you've never studied it before. In this video, we'll build the idea from scratch. We'll understand what matrix rank really means. Learn simple ways to find the rank of both small and large matrices, and then see why this one concept appears again and again inside modern AI models. By the end of this video, you'll have a much stronger intuition for how transformers process information and why understanding matrix rank makes the rest of the journey much easier. Let's get started. Let's start with a simple real life example. Imagine you ask five of your friends to describe a mountain they've all visited. The first friend says, "The mountain is tall." The second friend says, "It's very tall." The third says, "It's extremely tall." The fourth says, "It's huge." And the fifth simply says, "It's gigantic." Now, here's the interesting question. Did you really learn five different things? Not really. Even though five people spoke, they all described the same underlying idea. In other words, there was only one truly independent piece of information, and that's exactly the intuition behind matrix rank. And that is, how do we measure independent information from given set of informations? So, how do we measure the amount of unique information? In linear algebra, every row of a matrix can be thought of as carrying information. Sometimes every row contributes something new, but sometimes one row is simply another row multiplied by a number. In that case, it doesn't add any new information. It only repeats what we already know. Matrix rank simply counts how many rows or columns provide independent information. Notice what happened. The second row wasn't introducing a new idea. It was simply a scaled version of the first. Since there is only one independent row, the rank of this matrix is 1. So now we know what matrix rank really means. It tells us how much independent information a matrix contains. But why should someone learning transformers care about this? Because almost every important computation inside a transformer is performed using matrices: the embedding matrix, the query matrix, the key matrix, the value matrix, the feed forward network. They all transform information using matrices. And once you understand matrix rank, many advanced transformer concepts become much easier to understand. Let me show you exactly where. Let's try to understand why matrix rank matters in embeddings. Imagine I ask you to describe four animals: a cat, a dog, a tiger, and an elephant. But there's one rule: you're only allowed to use one characteristic: size. Using only size, the cat and the dog look almost identical. We've already started losing information. Let's add another independent characteristic: speed. Suddenly, the animals become much easier to distinguish. Now let's add one more characteristic. Is the animal domestic? Every new independent characteristic helps us represent the animals more accurately. Let's now look at the embedding matrix itself. Remember, every row of this matrix represents one word. Imagine many rows in this matrix become almost identical. That means different words are carrying almost the same information. The embedding matrix can no longer distinguish them effectively. Now imagine every row captures its own unique pattern. Each word contributes new independent information. The embedding matrix can now represent language much more richly. This is exactly why matrix rank matters. The more independent information a matrix can represent, the richer its representations can be. And that's why rank becomes such an important concept throughout transformers. We've seen that matrix rank tells us how much independent information a matrix can represent. We discovered why this matters for embeddings and why preserving independent information leads to richer representations. But embeddings are only the beginning. Every transformer is built from matrices: the query matrix, the key matrix, the value matrix, the feed forward network. Every one of them has a rank, and one mathematical tool lets us understand exactly how these matrices store information: singular value decomposition. Once we understand SVD, ideas like LoRa, QLoRa, low rank approximation, and model compression become almost obvious. That's exactly what we'll explore next.